Welcome to Study Loop.
Hi there. So for this problem, we need to calculate the angle that the loop 2 must be rotated so that the magnitude of the net field, magnetic field, is 100 nanotesla. So to do this, the first thing that we need to consider is the equation for the magnetic field of a circular loop, in this case a wire that is carrying a current. So that expression for a circular loop that is carrying a current, of course, is going to be of this form, where I is the current, the magnitude of the current, and R is the radius of the circular loop. So, since we have in here two concentric loops, and so we will have two magnetic fields, one that is produced by the wire 1 and the other magnetic field that is produced by the wire 2. So for wire 1, we will have this that is a constant, the current that is different over the radius of that loop. So on the other hand, we have for the loop 2 something similar, but changing the values of the current and the radius. So with this set, we can find these values because we are given all of this information in the data given for this problem. So we are going to do that. Remember that you need to transform all of these values to the usual units. So we will transform centimeters to meters and milliamperes to amperes. So for B1, we have the magnitude of the constant mu sub 0, which is 1.2 times 10 to the minus 6. We also have the magnitude of the current, which is 4 times 10 to the minus 3. And we also have this over the radius of the first loop, which is 0.015. So this gives us a value of 167.4 nanotesla. And for the loop 2, we will have the same constant, 1.256 times 10 to the minus 6. The current changes. The current of the second loop is 6 milliamperes, which is 6 times 10 to the minus 3. And this over 2 times the radius of that loop, which is 0.025 centimeters. This loop is, as you can see, is bigger, so it will be 150.72 nanotesla. Sorry. So these are the two expressions. So we are given that when we need to when we need to like obtain the net magnetic field, we need to consider this as vectors, and when we sum these vectors, we obtain a formula that from there we can have like the angle between these two vectors. So we are given for this problem that the sum of these two vectors should be equal. This is the sum of the two vectors and the magnitude of the sum of these two vectors. That's what we get in here. And this is equal to an scalar, which is 100 nanotesla. So we know that this expression can be written in the following form. The magnitude of the first magnetic field plus the magnitude square, of course, the magnitude of the second magnetic field square plus 2 times the magnitude of the first one, the magnitude of the second one, cosine of theta, where theta is the angle between the vectors b1 and b2. In this case, we are not working with vectors, but rather with the magnitudes, and the magnitudes we just have obtained it. So we just needed just simply to plot that values on here, and with that done, we can solve for theta. Doing that, we know that this is equal to this, so we just need to simply substitute all the values that we know. We know that the first one is the first magnetic field square plus the second one plus 2 times the first one times the second one cosine of theta. All of this. So to get rid of the square root, we can take for both sides the square, so that we will obtain this square, and we just simply need to solve for theta. So we can see in here that we will have something like this. We'll have minus this, oh sorry, it's in here, 6.4 minus okay, and all of this divided by 2 times. Now this is equal to cosine of theta, and from here, after plugging all of these values into the calculator, we obtain that the cosine of theta is equal to minus 0.807, and to obtain the angle, we obtain the cosine of minus 1 of that value, so that we will have that the angle is 143.8 degrees. And so this is the solution for the problem. Loop 2 has rotated through an angle of 143.8 degrees, so that the net magnetic field is of a value of 100 nanotesla. So this is it for this problem. Thank you.